Assalamualaikum. We are from Group 6. We're gonna present about the aircraft design evolution activity. The future aircraft that we choose is NASA X-57 Maxwell. We conduct a benchmarking by comparing the five electric aircraft, which is the NASA S57 Maxwell, Joby Aviation S4, HUD Aerospace ES30, Pipistrel Velis Electro, and by Aerospace E-Flyer 800. We compare key parameters such as aircraft type, propulsion system, cruise speed, range, payload, and wing configuration to understand the strength and limitation of each design. Next, we develop the several design ideas using the morphological matrix. After the generate the ideas, this allow us to combine the best features from the different aircraft and generate the five new aircraft concept. Finally, we evaluate this concept using the pure matrix concept, which is concept one used as a datum for the comparison. Each concept was assessed based on the criteria such as wing design, payload, propulsion, cruise performance, range, and operational efficiency. According to our evaluation, Concept 2 achieved the highest overall score because it provides the best balance of performance, flexibility, and efficiency. In summary, the NASA Maxwell is not intended to be the commercial aircraft. Instead of, it serves as technology demonstrator to validate the distribute electric propulsion, and while it has the limitation, it provides the valuable engineering knowledge that support the development of future sustainable aircraft.
Now I will present the aerodynamic performance analysis of the NASA S57 Maxwell. The first aerodynamic feature is the high aspect ratio wing. A high aspect ratio wing has a long wingspan and a narrow wing, giving it a larger wingspan to wing area ratio. As shown in the figure, the high aspect ratio wing on the left produces smaller wing tip waters than the low aspect ratio wing on the right. Since wing tip waters are the main source of induced drag, smaller waters help to reduce induced drag. As a result, the aircraft achieves a higher lift-to-drag ratio, allowing it to generate lift more efficiently while using less power during cruise flight. This helps to conserve battery energy and extend the flight range, making the S57 more suitable for electric propulsion. Second aerodynamic feature is the distributed electric propulsion. The S57 uses multiple electric propellers mounted along the leading edge of the wing. During takeoff and landing, these propellers accelerate the airflow over the wing, increasing lift at low speed. The additional lift improves takeoff and landing performance while maintaining good low speed controllability. Because more lift is generated, the aircraft can use a smaller wing without sacrificing.
Now I will present the propulsion system. The propulsion system of this Maxwell, this aircraft got the 860 pound of lithium ion cells to provide energy to the entire airframe. And then motor controllers, they use the silicon carbide controllers to convert DC to AC. And then it uses fly-by-wire. And then the type of engine this aircraft use, two large motors, two units, they produce about 60 kilowatts. And then the function is to forward velocity during cruise phase. And then another 12 smaller units which produce 13.7 kilowatts each, and they only use on the takeoff and landing. The advantage of this aircraft: blown wing lift augmentation, drastic drag reduction, vortex suppression, and also scale-free efficiency. The limitation of this aircraft is the electromagnetic interference, the parasitic wake, since it uses 12 high lift motors. Another is the thermal bottlenecks, which it relies on the passive convective cooling for leading edge motors. Since a passive system could not reject the intense heat. And then another is the energy density ceiling. Payload versus power, heavily ion battery, decimated carrying capacity, practical limits only restricted to seats and a maximum 1 hour of endurance.
X-57 retains the Tecnam P20060's aluminum fuselage. The real structural story lies in the wing, where a high aspect ratio composite structure and 12 distributed motors introduced load cases conventional wing design wasn't built to handle. The wing runs three spars root to tip, the front, main, and rear spars, carrying bending loads and supporting the control surfaces. At each nacelle station, Dedicated reinforced repairs transfer motor thrust and weight into the primary structure, while electrical wiring ducts run the full span without weakening the surrounding structure. Every nacelle position, in effect, demanded its own local structure. For the cross-section, each spar has a distinct role and form. The main spar is C-shaped, fabricated using carbon fiber with a high temperature Q, giving it maximum stiffness for bending resistance. The front spar, Z-shaped, acts as a protective shield for the main spar against propeller debris or bird strike and provides hard points for the nacelle attachments. The rear spar, also C-shaped, handles belt cranks and aileron hinge loads. The skin itself is carbon fiber with a quarter-inch PVC foam core cured at room temperature, a sandwich construction that resists torsion while keeping weight low. Running through the interior, you have separate power ducts for the cruise and high lift motors, plus an instrumentation ducts, all integrated into the structural layouts without disrupting the primary load path.
Moving on to the performance of the design, the aircraft cruises at 277 kilometers per hour with a range of 160 kilometers and an endurance about 60 minutes. It has a service ceiling of 4,300 meters with a gross weight of roughly 1,361 kilograms, powered by a 460 volt, 69.1 kilowatt hour battery pack. And the main goal of this design was never about speed, but it's about mainly about energy efficiency. The distributed propulsion setup gives us much better lift performance at low speeds and more efficient cruise, but that comes at a cost where the battery weight is much more significant and it directly limits how fast, how far, and how long the aircraft can fly. With that, the trade-off brings us to our key limitation: battery energy. Simply put, current battery technology can't store enough energy to support long flight durations the way jet fuel can. It gets even worse at the system level. The pack energy density is about 34% lower than the individual cell energy density, which means a chunk of the battery's theoretical energy is lost before it even reaches the aircraft system. The result is a direct hit to range and endurance of the aircraft, and for a fully electric aircraft, that's a major limitation that we have to design around.
Hi, this is Vasik, and let us quickly analyze the mission suitability of the NASA X-57 aircraft. So, the X-57 was not built as a normal passenger aircraft. Instead, it was designed as a technology demonstrator to test distributed electric propulsion and support future electric aircraft certification. This makes it very suitable for research purposes. Its main strengths are low noise, zero in-flight carbon emissions because it's electric, and improved efficiency. The high aspect ratio wing and distributed electric propulsion help reduce drag and improve lift, especially during takeoff and landing. NASA also used the project to generate important knowledge for future electric aircraft development. If we look at why it works and why there are limitations, the X-57 has major limitations. The biggest one is battery energy density. The batteries are heavy, but they still store limited energy, so the aircraft has short range and endurance. It also faces thermal management issues, electromagnetic interference, and propulsion safety concerns. These are serious challenges for safe and practical operations. So, overall, the X-57 is a highly suitable only as a research and certification platform, but it is not yet suitable for a regular commercial transport aircraft. Its value is mainly in proving that electric aircraft can work and in showing what still needs to improve. Okay, thank you, and moving on.
I'll be talking about our proposed design improvement. The most important challenge the X-57 faces is its short flight range. With a flight range of around 160 kilometers, it's not very suitable for regional transport or missions over 20 minutes. To overcome this limitation, we propose a hybrid electrical propulsion system. So, to its existing distributed propulsion system, we will add on a low weight turbo generator or a hydrogen fuel cell auxiliary power source. These sources would provide for either a way to recharge the batteries during flight or they'll work as an alternative source of power during flight. This greatly increases our available energy during flight without a drastic impact on weight or size. The augmentative nature of the system means we add on to the existing propulsion system and wing structure instead of changing it. and we want to keep the wing structure as it has good aerodynamic characteristics. Electric aircrafts are fairly new technology, and there are new regulations being made to address its reliability. So, the hybrid propulsion system helps keep up with that by making the aircraft more reliable and safer by introducing a redundancy which allows the aircraft to safely operate in case of a battery system failure. So, to summarize, we believe that the hybrid electric propulsion system is a suitable design enhancement as it addresses its range issues while also allowing for minimal design changes as well as increasing its reliability. This brings us to the end of our aircraft design evolution presentation for Group 6. Thank you for your time.